One of the big challenges with high-performance computing is working with terabyte to petabyte-sized data sets. Avere vFXT brings your large data sets closer to Azure Compute to limit latency and increase performance. Scott Jeschonek is here to show us how it works today on Azure Friday. Today on Azure Friday, I have Scott Jeschonek, who is with our Azure Storage team, to talk to us about the Avere vFXT, which we just announced as generally available. So Scott, can you talk to me about what Avere will do to help with my compute workloads?
Sure can, Lara. Thank you, by the way, for having me here today. It all starts with the ability to run what are called high-performance compute jobs. And so the idea behind high-performance compute is there's lots of different versions of HPC. Like, for example, I can run Hollywood scene rendering, and I'll talk about that in a second. I can look at genomic analysis. So I have got these genes. I've got to figure out how to line them up and figure out where the variants are. I mean, if you really want to go crazy, I want to simulate a thermonuclear explosion, right? So, there's labs that do that, apparently. And so these types of jobs are very particular because they run hundreds or thousands of virtual machines or machines in data centers. And these machines will come up and they want to read the same data over and over again as they're processing what's happening or running a simulation. And they may write out some results, and then they need to read those results. And so you've got this very intense, large-scale compute activity combined with a lot of potential storage that needs to be there very quickly.
Right.
And so, for example, I was mentioning media and entertainment. So in Hollywood, everything's based on, have you ever seen, I'll just say, any random movie that has animation? Okay,
right.
Maybe like Secret Life of Pets or something like that. Okay, well, everything that happens is a scene. And these scenes are consisting of thousands of frames of data. So when a dog moves from here to here, that's a frame and that's a frame. And they have to put these frames together and piece them together and render all of the assets that are in these frames. So like, for example, a leaf might be an asset, my shoe might be an asset. So all these assets come together and create these frames of data that then have to be built or rendered by like tens of thousands of cores of compute. And they need to do it in a fairly quick fashion so that they can build these movies. And one interesting thing is, visual effects shops work on schedules. And so they work with somebody and they say, we're going to get it done in this much time and it's going to cost this much money and so on and so forth. Well, things happen, right? And life happens. So the director comes back and says, I don't want a dog there, I want a cat, okay?
Right.
Suddenly they have to rework it. It bites into the schedule, and there's a lot of pressure on the shop to get things done even faster. And so, the ability to run as fast as they possibly can each time they have to render something is critical to their business. And then the other aspect of it.
So to do that, they need more compute at times, or
That's exactly right.
They need to have some agile access to lots of compute to dial up or down those timelines.
That's right, and this has been a historical problem. So, in the days, and it still happens, I think, to some extent, a render shop might lease racks of servers, and a truck will back up to the data center, and they'll put these racks in, and they hook them all up, and they run these things, and that helps them get through that sort of burst problem that they had at that time. But even that's very, it's labor intensive. You have to figure out how to do it. The cost might be good, but you have to make sure it's available. So if you're renting from X, hopefully they have what you need. That's been a real problem. And so how to take care of these peaks, but also how to maybe do more work. So as a visual effects shop, maybe I can do more scenes for more movies with more assets if I have more flexibility with how I do compute. And so they're very interested in running compute jobs in cloud. But the type of compute jobs that you have to run in cloud, whether we're talking about Hollywood or we're talking about healthcare, like for genetics, I want to run in the cloud. It's all basically the same problem. I want to run thousands of cores of compute, and I need to get very fast access to certain data. And the key is that data may be here, in my data center. It may be in the cloud. It may be in both places. How do I do that? How do I get that low
data
latency?
is huge.
It can be quite large, right?
Yes.
So, a reference genome could be hundreds of gigabytes in size, or it could be very tiny in some cases, depending on what you're looking at. Like the human genome is much larger than a worm genome in some cases. And so that data has to be presented to all of these compute nodes as fast as possible. And so where Avere comes into the picture is we offer you the ability to do what's called bursting or hybrid cloud. You can run the Avere system in Azure Compute by your new compute farm that you're building virtually, and it can then present the data to that compute farm in a fast way. And the way that it kind of does that is it doesn't get every piece of data that's on-prem, it only gets what the clients have been requesting. And the chances are in your typical HPC job that the data itself is going to be requested again and again and again, and that's the key, right? Is it's there, it's already in the cache layer, in the Avere layer, and it's fast.
Okay. Okay. Well, can you talk to me a little bit more about where your data could be stored? You mentioned you've got data on-prem, but I see you also have support for Azure Blob.
Yes, absolutely. So in the classic case, we'll call it the classic code case, right? A lot of customers, they have embraced the cloud. You know, I think we're all done with the to cloud or not to cloud thing, right? Everybody's pretty much on board. It's a question of how do they move into the cloud in a way that everybody's happy with, and that that they can do things right away, and it doesn't impede on their current business. And so, for example, a customer might have a lot of network attached storage sitting in their data center, and it could be like petabytes, and we call that sort of a data gravity issue, where it's like I've got petabytes of data down there. How do I move that data up into the cloud? Azure certainly has some solutions with DataBox and some other things that can help you move that data up, but it's not always a technical problem. A lot of times it's a human factors issue where it's like, there may be regulatory issues, there may just be politics, concern about moving all the data up and overcommitting, or it's just a time problem where it's like, yeah, we know we need to move it, but I don't need to move it right away. I really would like to use that compute farm though. And that's where you can say, okay, fine, I don't need to move all of my data. I don't have to make that commitment today. I can run Avere in the cloud and get you that burst use case. Right. On the other hand, there are customers that they want to move data into Blob because Blob is a great product, it's a great service, it's low cost, and it's highly available, and all those nice things. But one of the things that we've seen over time is they're very concerned about moving their data up and having to change their code. So like, your typical HPC job is running and it's looking for data at a path in a file, well, Blob is object-based, and so I would, as a data analyst, if I wanted to move my job into the cloud, I'd have to re-architect my job to run it into the cloud. So what Avere can do then is we can basically leverage Blob as basically a NAS. Oh. And so you can move a petabyte of data or 2 petabytes of data into the cloud. You can move it behind the Avere, and the Avere provides like an NFS NAS for your HPC job in Azure Compute.
So it becomes more transparent for moving existing workloads up to the cloud without having to change your code.
That's right.
That's beautiful.
Yep.
Yeah. Okay. And as you move up to the cloud or even anywhere, machines go down. Can you talk to me about what happens? Are we protected? Is there high availability?
Machines never go down in the cloud, Lara, come on. No, I'm just kidding. And this is another historic problem. This is not just a cloud problem. So, you have a visual effects shop, they have a 10,000 server farm, and they're ready to run a job, go. And let's just say that you don't have an Avere in the mix, and all of a sudden the network link goes down to the storage, oh my. Then your job has just failed, you've lost valuable time. And so historically, Avere has always been a highly available cluster. So you run multiple Avere appliances in the classic on-prem use case. In the cloud, it's the same thing. So you run a minimum of 3 Avere nodes sitting in Azure Compute, and basically you'll use something like round-robin DNS to distribute the client connections to the vFXT cluster. And then if a node happens to fail on our side, it's not a problem, because what we'll do is we'll basically move the IP address that's bound to the NIC on the virtual machine that we're running on to another one of the cluster members. And so any clients that we're connecting to that IP address, they just keep connecting and going.
Great, great. Well, do you want to show us how this works?
Sure, be happy to. So if I go in, so this is sort of like a cooking show where it's like, okay, it's already done, the lasagna's out of the oven, but I did this before we ran just because it takes more time than probably we have to run it. But this is our dashboard, and this is our historic dashboard. You get this on the virtual FXT. We also have a physical FXT, and it's the same thing. So it's the same experience both ways. And what you're actually seeing here is a histogram of read throughput.
Okay.
And what I mean by that is I basically, and I can go over here very quickly and show you, I have run 12 DS machines with a high performance file testing mechanism. So they all connected to the Avere cluster, and they were all asking for a bunch of data. And so we were able to pump out around, peaking up at around 250 gigabytes per second throughput on my simple test. If I back this up a little bit, I'm going to go back an hour, you can see the whole test. And so this was basically, the test wrote some data into the cluster. And by the way, what you're seeing here is an Avere vFXT cluster sitting in Azure Compute on 3 nodes. I'll go up here and show you that. Here they are, Avere cluster 1, 2, and 3. And these VM test instances are all mounting that Avere cluster. And basically, the test kicked off and it wrote about a gig worth of data into the system, and then all 12 of those nodes just jumped onto the Avere and started asking for a bunch of data and reading it. And so you can see that you can get fairly reasonable throughput. This is just an example test. I mean, the types of scenarios that we've seen customers run are, this is a 3-node Avere cluster. We've seen customers run 12 nodes of Avere, getting around 1.7 gigabytes per second per node
Great.
of throughput, and being able to scale to tens of thousands of NFS connections across this. So you have to think of this as a file performance tier that sort of is just invisible, and when it's working,
cache.
Exactly, it's a cache.
It's a cache.
When it's there and it's doing its job, you're just happy and your
Yeah.
jobs are running quickly.
Okay. Okay.
So I can take you through a couple of other data points about this. So I'm going to pivot over to slides very quickly just to walk you through a couple of things, and then I'll go over to the UI to show you what they are. So a couple of details, and this is as of GA. So we are only clustered, and typically you'll run 3. You can run as many as 24, odd number, but that's our tested production number instead of a theoretical maximum number that nobody ever tested. And so that's sort of the max, but our average is about 6 to 7 or 8 nodes. But you can run quite a lot of load against a 3-node cluster or a 6-node cluster. We have a customer that was doing a movie render. They were using 6,500 cores on average all day, every day for a couple weeks, and happily doing so. As we said, the high availability is important for a couple of reasons. One reason is because, as I said, if a node fails, that can impact an HPC job, and nobody wants that impact, so you want the reads to continue, so the clients are able to continue. On the other hand, if you're writing out data from the HPC cluster through the Avere system, you want to be very cautious about protecting the writes. And so every write that's written through to the Avere cluster is immediately cloned to another member of the cluster. So there's an election process, and everybody's a partner.
Right.
And then that means that in the event that the primary node that client was connected to happens to fail, the write, we'll call it a dirty write, is preserved and protected. And then there's a new election, and then that's cloned to another HA partner.
Classic architecture. Good.
Some just basic details. So how do clients connect? We have this thing called a vServer, and this is sort of the export point for the file system from a client perspective. So clients are connecting through this vServer mechanism, and if I go over to the UI, I can show you down here. We have a vServer configured, and you'll see there's a range of IP addresses on the vServer. That IP address is essentially what a client would use to connect to the system.
Okay.
And then ultimately, I think the clients should not, they're not connected right now, but I can always get that to happen again. We'll give that a minute to fire back up. And so the vServer basically is the place where clients will send their NFS requests, and the vServer then services that and sends it back to our caching layer, and that's how clients interface with the system. Then there's this notion of a core filer. And the core filer, so what's nice about our cache is not only does it lower latency and increase performance, but it provides a little bit of flexibility in terms of accessing the data itself. So if I go over to the actual system, I'm going to scroll up here for a second and go into what's called the core filer. What I can basically do is I can attach in multiple sources of data. So if I have a NetApp sitting in my data center and it has an export, I can put that into as a core filer. If I want to put a blob container in for like scratch space, or I want to put reference genomes in that, I can connect that as a core filer, all into the same system. And you can have anywhere reasonably from 10 to 20 core filers connecting sources of data from various places. And this is what a core filer configuration looks like in our system. This one here, MS Azure, is the Blob core filer. You see it has this notion of a cache policy. That's a technical thing for a class. We welcome anybody to go and look at our documentation or our videos, and you can see how to configure that. The key thing is you can see right here it has a 1 hour write back delay. What that does is if you're running an HPC job and you have to write out what are called intermediate results, a lot of times the pipeline has to wait until that's acknowledged before it can continue on. This write back timer allows the cluster to immediately act to clients and then move on, and then within an hour it'll flush that data to the back end.
Great.
And then just last couple things, you can see I'm talking to a blob container. I had to find a unique name, so I always use my last name is very unique, and then basically uses an MSI cloud credential to connect to that container and put that into the system. And you'll see I also have another core filer configured. So that was the Blob core filer, and I just threw together a Ubuntu NFS server sitting in Azure Compute and enabled an export on that, and you can see there is that particular system. And if I were to go to a client, all right, and I break my demo, hang on, thank goodness for edits. This is the part they edit, right? So if I go to, in fact, this is a client, and I'll just give you a quick show of what a customer would look at. So this mount command shows you the various file systems that this particular client is aware of. And you'll see I have 3 mount configurations. Basically, these 3, you see 10, 0, 0, 12, 14, and 13. Those represent that V server that I was talking about, right? And those are different mount points that this particular client sees. And if I change directory to one of those, you'll see that there's the 2 core filers I was referring to. So the MS Azure is the one that's running the test that you see in the background. And that's under here. And you can see test run, next 12.
Those are all the individual files that were
That's
brought
right.
in.
So everything's getting pumped.
Okay.
And then on the other hand, if I go to NFS dir, this is the actual NFS filer that I mentioned, and I have exported to that. These are actually genome reference files, and these are all sitting on that other NFS server. So this is a particular case where I have a blob container with lots of files, and I have an NFS server with other files, and so you can see, like an example for life sciences would be, I put all my reference data in the blob container and have it sit up there. At a nice low cost. And then if I have to, I can reach back and get the customer data for the processing of that analysis, but then the reference genomes are already up in the cloud and I can have a nice low latency experience.
Great. Well, where can we go learn more about how to use this and integrate this into our HPC workloads?
Great question. So where we are as of our GA is in the handy marketplace, the Azure Marketplace. Here it is. You'll notice that there's some information about plans and pricing. Here's a very good data point for you. So we do run elsewhere, but primarily we're focused a lot on Azure these days. But the nice thing is from a cost perspective, the only thing you have to pay for with regards to an Avere system are the actual underlying virtual machines and disks. There's no additional license cost to run the vFXT in the cloud. So if you're interested in trying it against an HPC workload, and you're able to run, whatever 3 E32S v3s or something like that, you don't have to worry about an additional license.
Fantastic, fantastic. Well, thank you very much for joining us today and sharing all the great news about Avere vFXT, and we look forward to using this in our HPC workloads.
Lara, thank you very much.
All right. Today we've been learning all about Avere vFXT on Azure Friday.